Welcome to our quantum deep dive. Today, we're digging into a question that has kept physicists up at night for decades. How in the world do you build a computer that can't be broken? We're going to explore a really wild answer, all through the lens of one brilliant physicist, Alexei Kitaev, and based on a fantastic essay by Georg O.A. Schnippet. Right, so we're talking about the work of Alexei Kitaev, a physicist who looked at this problem and didn't try to solve it head on. No. Instead, he came up with a revolutionary answer that just sidesteps the whole problem of breaking in the first place. But to get how he did that, we first have to understand why quantum computers are so incredibly fragile to begin with. Okay, to really appreciate the genius of what Kitaev pulled off, you first have to get a feel for the central, almost tragic challenge of quantum computing. It's this story of unbelievable potential and just devastating fragility. Think about it like this. You've got your classical bit. It's a rock. It's simple, it's stable, it's either on or off, a 0 or a 1. It's the dependable workhorse of all the technology we use every single day. And then you have the quantum bit, the qubit. This thing is a powerhouse. Because of a property called superposition, it can be a 0, a 1, or some mind-bending combination of both at the exact same time. That's where all the insane computational power comes from, but it's also its Achilles heel. Yeah, that fragility really comes down to one word that absolutely haunts quantum engineers: decoherence. It's the constant, unavoidable chatter from the outside world. A tiny vibration, a stray magnetic field, the slightest change in temperature, any of it can make that delicate quantum state just collapse and completely wreck your calculation. It's like trying to conduct a beautiful, complex symphony in the middle of a hurricane. That's the scale of the problem everyone was trying to solve. So, faced with what looked like an impossible task, the whole field was focused on one thing: building better shields, colder refrigerators, more clever ways to isolate these delicate qubits from the noisy world. But Alexei Kitaev didn't ask how to build a better box. He asked a completely different and way more profound question. And, to really get the question he asked, it helps to know where he came from. Kitaev was born in Moscow in 1963, and he was a product of the legendary Soviet School of Physics, specifically the Landau School, which was famous for its intense rigor and its focus on first principles. That training basically taught him to strip problems down to their absolute core. Now a professor at Caltech, he brought that unique way of thinking to this problem of quantum fragility. And this is it. This is the revolutionary question he asked. While everyone else was trying to protect the individual musicians in that orchestra from the hurricane, Kitaev was wondering, what if the music wasn't played by the musicians at all? What if the music was woven into the very shape of the concert hall itself? What if the information wasn't in some fragile local property of one qubit, but in a global, holistic property of the entire system? The answer he found, the tool he needed to weave information into the very fabric of reality, wasn't just in physics. He found it in a beautiful, abstract branch of mathematics called topology. So topology is all about the properties of an object that don't change when you stretch it or bend it. The classic example you always hear is that to a topologist, a coffee mug is the same as a donut. Why? Because they both have exactly one hole. You can't get rid of that hole unless you physically tear the object. And here's the really cool part. Having one hole is a global property, not a local one. You can't tell it has a hole just by looking at a tiny piece of the mug. You have to see the whole thing. And that's what makes it naturally tough against little local pokes and prods. This is the heart of Kitaev's big idea. Kitaev laid this all out in his famous toric code model. It's basically a brilliant blueprint for a quantum computer that is naturally immune to errors. So picture a grid of qubits living on the surface of a donut, a torus. The actual information, the 0 or the 1, isn't stored in any single qubit. No, it's encoded in a global pattern, like whether a whole loop of spins wrapped around the donut's hole is pointing up or down. Now, if a random error comes in and flips just one qubit, it doesn't change that global property. What it does is create a pair of tiny detectable glitches, these things called anyons. But the crucial part is the information itself is totally safe, shielded by the overall shape, the topology of the system. Okay, so if the information is stored in the shape of the thing, how do you actually compute with it? I mean, you can't just go in and flip a single qubit anymore. You need something totally new, something that can play with these global properties. This new kind of computer had to be built with ingredients that, at the time, were pretty much purely theoretical: exotic quasi-particles. And these are the anyons.
those little disturbances we just mentioned. It turns out that in two-dimensional systems, particles don't have to be just bosons or fermions. They can be something in between. Something, well, anything. And they have this incredible, almost magical property. When you physically move one anyon around another one, their combined quantum state changes in a very specific, predictable way. This process is called braiding, and it's like a cosmic dance. The act of braiding their paths through space-time is the computation. And it's naturally fault-tolerant because it doesn't matter what the exact wiggly path of the dance is. All that matters is the topology of the braids, who went over and who went under.
But Kitaev's exploration didn't just stop in 2 dimensions. He also wondered what might happen in a simpler, one-dimensional system. And this led him to another huge proposal, the Kitaev chain. It was a model for a special kind of 1D superconductor that could be the perfect home for a different type of exotic particle, one that was ideal for this new kind of computing.
Right, and these are the Majorana fermions. These things are incredibly weird. They're particles that are also their own antiparticles. In Kitaev's one-dimensional chain, they pop up as a pair, with one at each end of the wire. A single qubit can then be encoded in this pair of well-separated Majoranas. And because the information is stored non-locally, it's split between the 2 distant ends of the wire, it becomes almost impossible for some local noise at one end to mess up the data. It's basically the ultimate form of social distancing for your quantum information. So what started out as this beautiful, elegant bit of mathematics on a blackboard, well, it definitely didn't stay there. Kitaev's ideas provided a concrete blueprint, a real roadmap that has since kicked off a global quest to build a working topological quantum computer. And you can already see its impact today. And that impact is absolutely huge. Historic code is the direct ancestor of what we now call surface codes, which are being used by companies like Google and IBM right now to try and stabilize their qubits. The hunt for his Majorana fermions, that became the entire mission of Microsoft's massive Station Q project. And even his earlier work on an algorithm called quantum phase estimation is now a fundamental building block for some of the most powerful quantum algorithms out there, like Shor's algorithm, the one that could potentially break most of our modern encryption. For all of these game-changing contributions, the scientific community has, quite rightly, recognized his genius. In 2012 alone, he got both a MacArthur Genius Grant and the super prestigious Dirac Medal. Then, in 2015, he was awarded the Breakthrough Prize in Fundamental Physics. And these aren't just trophies for the shelf. They're a real testament to just how profoundly this one person's ideas changed the entire landscape of a field. So let's bring it all the way back to that initial, seemingly impossible problem. How do you build an unbreakable computer? By having the courage to ask a different question. By shifting the whole paradigm from protecting the parts to encoding in the whole, Alexei Kitaev gave us the most profound answer imaginable. He told us, don't fight reality's messy tendency to disturb things. Instead, build your computer from the resilient, unchanging, topological fabric of reality itself.
And that leaves us with one final, truly mind-bending thought to chew on. What does it mean for our technology when the line between information and the very geometry of the universe starts to blur? Our exploration today was based on the comprehensive essay Alexei Kitaev, Ford and Denker, Their Topological Quantum Welten, by Jörg Owe Schneeppet. To read the full text, you can visit schneeppet.de. Thank you so much for joining our quantum deep dive. Goodbye.
Schneeppet.de is a private project by Jörg Owe Schneeppet dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.